Let us complete our study of Myhill-Nerode relations and other related things in this lecture. Recall that. So we start with a recapitulation and equivalence relation. Okay. For some language R, we earlier considered this to be a regular language, but from time to time we will lift this restriction. Anyway, an equivalence relation, okay, on sigma star on sigma star is called a Myhill-Nerode relation for some language R if the following three properties are satisfied. First, this is a right congruence, which implies that if x is equivalent to y for two strings x and y, then for any a in the input alphabet, they must also be equivalent. Okay, so for all a in sigma, in fact, this essentially generalizes to this x congruent to y or equivalent to y. If that is the case, then we have xz equivalent to yz, and this is for all z in sigma star. So this will follow from this original property of right congruence by induction on the length of z. Second, this relation refines R in the sense that if x is equivalent to y, then x belongs to R if and only if y belongs to R. And finally, this is an equivalence relation, so it has a number of equivalence classes. The number of equivalence classes is called the index of the equivalence relation, and this has finite index. Okay, and we let us introduce a new thing, an equivalence relation this on sigma star is called, let us say, a Myhill-Nerode prime relation for R if this relation satisfies 1 and 2. So we are not enforcing condition 3. Okay, so it's clear that every Mn relation is an Mn prime relation. But if this is not a finite index, then we do not call this relation, this Mn prime relation, an Mn relation. Okay. Okay, so this is what I am going to use, Mn and Mn prime relation. So the only difference is that I am not imposing the restriction of finite index on an Mn prime relation. And we will see this still makes enough sense. Okay, so you also recall that we have a construction or a couple of constructions A given a DFA M without any inaccessible states. We constructed an Mn relation for it. Moreover, given an Mn relation, we have constructed a machine M, okay, whose language is precisely this R. Okay, and we have also seen these constructions are of inverses of one another. Okay, so these are inverses of one another, which means that if I start with a machine, generate an Mn relation, starting from that Mn relation, if we prepare the machine, this machine and this machine are essentially isomorphic. Also, if I start with an Mn relation, generate a machine, and consider the corresponding Mn relation, then this and this are exactly the same equivalence relation on sigma star. Okay, but the point is that in all this effort, whenever we have this equivalence relation on sigma star, we have a machine involved. Machine, of course, here means DFA involved in the construction. Here, for example, we start with a machine, and here, given an Mn relation, we construct a machine. So now I am going to define a relation using R alone. Okay, that is using the strings in R and sigma star and without using any machine whatsoever. Okay, so that relation is going to be a property of the language. Okay, and that will essentially help us in proving several important properties about regular languages. Okay, so now I just define something like this. Let R be a language over sigma, not necessarily regular. I will later specialize to regular languages. Okay, now I define an equivalence relation with respect to this R as follows. Okay, we say that two strings X and Y are equivalent if and only if for all Z in sigma star I have this XZ is in R if and only if YZ is in R. So I am not using any machine for defining this. So this equivalence relation is a property of the language R itself. Okay, and in fact I will now show that this is the best possible relation that we may have. Okay, so let us look at some properties of this. First, maybe lemma. this is an Mn prime relation. So for this moment, I am not imposing the restriction that R is a regular language, and therefore I am not talking about the question of finite indices and so on. Anyway, this still satisfies properties 1 and 2. Okay. So first of all, it should be a right congruence. Why? So this is the property. So for example, if I take z equal to AW, then this condition implies that, okay, so suppose that x is equivalent to y with respect to this relation, then since this A and a W are arbitrary, okay, I can say that for all A in sigma and for all W in sigma star, I have x A. So I have replaced z by AW. So I just write xa W is in R if and only if ya W in R. And sorry, I made a small mistake. This is not exactly a two-way implication. This is a one-way implication. Okay. Now, if I look at this xa and ya, these two strings, it says that for all W in sigma star, this appended by W is in R if and only if this appended by W is in R. Therefore, by this definition, we can say that for all A in sigma, we have xa equivalent to ya. But that is precisely this. If x is equivalent, xa is also equivalent. And this is the proof. And also I have to show that this refines R. Why? What is the definition of refinement? Two strings are equivalent implies, sorry, this one. Two strings are equivalent implies x is in R if and only if y is in R. Okay. So this is the definition. But this follows, if these are equivalent, then this is true for all z. In particular, I can take z equal to epsilon. And it will show that this is true for all z. So in particular for z equal to epsilon, this will show that x is in R if and only if y is in R. Okay. So this is a Mn prime relation. So the finite index thing I am not yet considering. Okay, I will later specialize to regular languages. Okay, so I start with another definition. Suppose that this and this are two equivalence relations. Then we say that this refines the second equivalence relation if this is contained in this. So recall that we have defined and or a binary relation on a set A as a subset of A cross A, right? The Cartesian product of A with itself. And therefore this and this are essentially sets. So this is basically set inclusion. It makes sense to talk about this. So maybe as an example, of course we have seen several examples in the previous lecture. So let's say congruence modulo 3 is or refines no, congruence modulo, let's say 6 refines congruence modulo 3. Now we are talking about equivalence relations on a set of integers. Okay. So that means if two integers are congruent modulo 6, then they are definitely congruent modulo 3. Okay. So this is contained in this. Now what is important about this relation is that if we have any mn prime relation, okay, and we have an mn prime relation defined using the given language R, there is a relation between this. So this is our second, I would say, did I use lemma? Yeah, second lemma. Let R be as before, a language not necessarily regular, but if this is an mn prime relation, for R, then this refines R. So what is the proof? Okay, suppose that this is an mn prime relation. So I say that they are equivalent. This implies this implies yeah. What does it imply? By definition, okay, so this is an mn prime relation. So I have this right congruence, okay, and it's I will use this result. Okay, for all z in sigma star, xz is congruent to yz. Okay, implies for all z, xz is congruent to yz, but z is in sigma star. For all z, this is true. And then, since this is also an mn prime relation, so it also refines R. So that means by property 2, this implies for all z, xz is in R if and only if yz is in R. But this is precisely the definition of congruence of x and y with respect to this relation. Okay. So this any mn prime relation will be included in this relation. So what does it imply? This implies that, so So this implies, so that's the end of the proof. But this implies this is the coarsest Mn prime relation for R. Or for that matter, I can say A. Okay. A coarsest, where coarseness is with respect to the number of equivalence classes. The smaller the number of equivalence classes, the coarser this equivalence relation is, and the larger the number of equivalence classes we have, the finer the relation is. Okay, this is with respect to equivalence classes. Okay. Now, of course, if there are two coarsest Mn prime relation for the same language R, then by this lemma I have this contained in this, and also by this lemma this is contained in this. Okay, so this implies these two relations are essentially the same. Okay, so that means the coarsest Mn prime relation for R is unique. Okay, so instead of A, I can now use D. The coarsest Mn prime relation. Okay. Okay. Now, with this tool in hand, I now specialize to regular languages. Okay, so maybe I use a new page. Okay, now this is called the Myhill-Nerode theorem. For a language R, over sigma, the following are equivalent. First, R is regular. B, R has a Myhill-Nerode relation, and this relation has finite index. Okay, so we have done most of the things to prove this. Fairly straightforward. So A implies B. Since R is regular, there is a DFA M for R. Then if we apply the construction DFA to an Mn relation, you can see this M is a Myhill-Nerode relation for the language of this machine, which is R. This is straightforward. Okay. Then what about B implies C? This has a Myhill-Nerode relation. Okay, let's say this is a Myhill-Nerode relation. For R. Then by the last lemma, this refines. Okay, so this implies this is also a Mn prime relation. But then this refines this Mn prime relation, this. Okay, since this is coarser, this is finer. Okay. And since this is a Mn relation, this has finite index. Okay. And this is possibly coarser than this. So this implies, so this is no finer than this. And since this is an Mn relation, in addition to being Mn prime, this has finite index. And since this is potentially coarser, so this is also, therefore, of finite index. Okay. And the final part, C implies A. If this is a finite index, then if we use that reverse or converse construction that builds a machine M, okay, this is now a DFA. Why? Other things are clear. Since this is a finite index, this means this has finitely many equivalence classes, and the states of the machine are these equivalence classes. So this machine, which behaves like a DFA, also has a finite number of states. Okay. So that's the end of the proof. This is fairly straightforward, given all the tools we have developed so far. First of all, the importance about this theorem is that this is an if and only if condition that avoids any machine. So I have never used any machine in the statement of this theorem. Okay. Of course, during the proof I have used some machines, but that's okay. The statement does not make use of any machine. So this is an if and only if condition. In particular, it says that a language R is regular if and only if the corresponding Myhill Nerode prime relation, this has finite index. Okay. So this theorem can therefore be used to prove both regularity, that is by showing that this relation has a finite index, or R has an Mn relation, okay, with finite index, and this can also be used to prove, or instead of irregularity I write non-regularity. Oops. So we will see an example. Recall that pumping lemma is only one way, okay, because there exist languages which are not regular and they still satisfy the pumping lemma. Okay, so that's not an if and only if condition. Okay, but this Myhill Nerode theorem gives us an if and only if condition for recognizing regularity versus non-regularity. Okay, moreover, I have this very important I would say this very important application. So application 1, Okay. Consider, let R be a regular language. And let let M be a collapsed DFA for R. Okay. Then if I define this with respect to this, then this is same as R. Okay. So this says that the collapsed minimized DFA is defined essentially by this relation, and which is independent of any machine. Okay, collapsed DFA. Of course, I always assume in this context that R has no inaccessible states. Why? So, let me prove this statement. Okay. So, since this is a collapsed DFA, it cannot be collapsed further. Okay. So, if I now define the relation to states P equivalent to Q, if and only if you recall this definition of equivalence of states, if and only for all Z delta hat PZ is in R, if and only if delta hat QZ is in R. Okay. And since this cannot be collapsed further, this is equivalent to saying that P is equal to Q. Okay. No further pairs of equivalent states do exist, and therefore this equivalence relation on the set of states that we have used is essentially the equality relation or the identity relation. Okay. So now let us prove that these two relations are essentially the same. So I start with maybe this. Take any two strings x and y. They are in y. They are equivalent with respect to this. I have to show they are equivalent also with respect to this. So y, this is if and only if, by definition for all z in sigma star, what is the definition? xz is in R if and only if yz is in R. This is the definition of this relation. Okay. Now, this says, now this is equivalent to saying that delta hat, if I apply delta hat on xz, it will be in f if and only if I apply delta hat on yz, it will be in f. Okay. So delta hat of x, start from s and then xz. This is in f if and only if delta hat starting from s yz. This is in f. Okay. This is by the definition of DFA. Okay. Because this accepts R. Okay. So therefore this must be a final state if and only if this is a final state. Then I use this. this is same as saying delta hat first apply on X, then Z. This is in F, if and only if. I write this also in the same way, delta hat first apply S, Y. This is in Z, this is in F. Okay. Now if I consider this state P, and if I consider this state Q and use this, okay, so delta hat PZ is in, sorry, R is actually a string, so I should not have R here, I should have F here. This is a final state, if and only this is a final state. This is how we have defined it. Okay, it makes no sense to write R here. Okay, so if I now use this, delta hat PZ is in F, if and only if delta hat QZ is in F. Okay. Okay. So from this, it follows that this and this, they are equivalent, right? But then since the machine is already collapsed, this is equivalent to saying that delta hat Sx is equal to delta hat Sy, and by definition of this follows that this is if and only if x is equivalent to y with respect to this Mn relation. Okay. Okay. So a tuple belongs to this relation if and only if it belongs to this relation. So a collapsed automata without any accessible states, okay, corresponds to exactly this relation, and that is independent of any machine. This is defined in terms of this language, and therefore it follows that the minimized DFA is unique. And of course here uniqueness is up to isomorphism. Okay. And then, so that's a big thing that we wanted to prove. The final proof is now ready. And here is a second application. This is of a different kind. Okay. I will show that the language a power n, b power n, such that n is greater than or equal to 0 is not. So let us call this language A is not regular. So I will prove this by looking at this. And in particular, I will show that this does not have, this is not of finite index. And since the Myhill-Nerode theorem is an if and only criterion for regularity, this will prove that this language is not regular. Why this is not a finite index? So consider the equivalence class of a power k and the equivalence class of a power l. Okay, k not equal to l. Okay. Now, if I consider z equal to b power k, then you see that a power k, b power k is in A, but a power k, b power l is not in A. This implies that there exists at least one string such that this is in A, but this is not in A. Likewise, if I take b power L as Z, this will be in L. If I append b power L with this will be in A. This will not be in A. Okay. This implies the equivalence classes are not the same. So in particular, it says that there are at least these many equivalence classes. What are these many? The equivalence class of A power 0, which is not the equivalence class of A power 1. This is not the same as the equivalence class of A power 2. Okay, so these are all distinct from one another. Okay, so these are all distinct, so therefore this is not a finite index. And since the Myhill-Nerode theorem is an if and only if criterion for regularity, it says that A is not regular. Okay, so we will see more applications of the Myhill-Nerode theorem and the Myhill-Nerode theory in the tutorial sessions. So this is basically a very interesting result about regularity. Let me stop here. From next class onward, we will start our study on context-free languages. This still leaves us with many, I would say, interesting topics untouched. One possibility is, so far we have been talking about minimization of DFA. Okay. So what about minimization of NFA? Okay, of course, this is also an interesting topic, but we have to proceed to the other parts, other types of languages. So I will not consider this question further in this question. Not further, this question I will not consider in this course. Okay, so you can read one section on from our textbook by Kozen, which says something about minimization of NFA and similar things. The problem is that for NFA, the theory does not remain as neat as for DFA. Anyway, so if you are interested, you just see our textbook, Kozen. Okay, and many other places. Okay, so with this, I would like to stop. So from the next lecture, context-free languages will be introduced. Okay, so bye.